Let me tell you about something really cool. And by cool I mean about negative 273 degrees Celsius cool. Quantum computers, where they place nuclei, electrons, or even light in a computer. In classical computers, information is stored in the form of bits, 0 or 1. In quantum computers, it can be in any combination or superposition of both.
A quantum bit or qubit can be an electron spin in a magnetic field. If spin up is 1 and spin down is 0, then spin sideways is in a superposition of both spin up and down, and so of both 0 and 1. So compared to classical computers where the amount of information is limited to only the number of bits, with superposition it is 2 times the number of qubits.
Now if we entangle those qubits, the power becomes overwhelming.
Quantum entanglement is simply a very weird relationship between quantum objects in superposition, where for example the measurement of an electron at Earth simultaneously influences the other entangled electron at Zorg, regardless of the distance. An everyday object such as a three-headed dragon can be compared to 3 entangled qubits. They are strongly correlated that they become inseparable. Therefore, you must think 3 heads at a time, since separating them kills the dragon. Consider wearing a mask to be 1 and not wearing it to be 0. All or none of the heads may be wearing masks, or any possible arrangement in between. So, we have a superposition of 8 different states. Find the 4-headed dragon and it has 16, and so on. To get a sense of how powerful that is, imagine that your coach forced you to do 2 push-ups in the first day of quarantine, and the next day double the number of push-ups you did the day before. After a month, you will have to do about 1 billion push-ups, compared to 30 when you increase it only by 1. So compared to the linear increase in classical computers, the computational space in quantum computers increases exponentially as we increase the number of qubits. So it is when we entangle the qubits that the true power appears. There is a problem though. When we try to see or measure the superposition, it gives us one random answer.
So in order to make sure we got the right answer instead of just a random one,
quantum algorithms plan the problem in such a way, creating superpositions along different paths, where paths to the wrong answer cancel out and paths to the correct answer add up.
this leads to exponential speedup since we can now make use of the superpositions created in our computation and then extract the correct answers of our measurement, giving us the ability to solve certain types of problems that take thousands of years on the most powerful classical computers in a day or much less. Seems perfect? No.
These qubits are extremely fragile, and any external noise interacting with them will lead to high error rates. That's why most quantum processors must be isolated and stored near absolute zero.
Because of this problem, we are still trying to reach a perfect 100-qubit system. But if we can make a large enough system, we might be able to advance in areas like machine learning and artificial intelligence, introduce a safer quantum encryption, or even develop better drugs by simulating the quantum interactions at the molecular level more accurately. But getting to see how well quantum mechanics work is certainly the biggest win.